This is Algebra Lesson 7-6, Exponential Functions. Please make sure you have your yellow note packet out. Your first slide should look like this. These are the exponential growth and decay models that we're going to be covering in this lesson. Y equals AB to the power of X. Notice the yellow box is the same on both slides. The first box represents exponential decay. So our value is starting at a high number. Notice it starts at 100, and it is decreasing to 50, to 25, to 11, to 7, and so on. And it just keeps getting smaller and smaller. So the decay factor, which is this B value, has to be less than 1 because it's going to get smaller. The exponential growth model, notice we're starting at almost 0, and then we're getting bigger. Here's at 4,000. Here's at 8,000. So with one space, it looks like we're almost doubling our population, and that's where this number comes in right here, the 2, and it turns out that we are doubling. So we're starting with 1, and then it doubles every time. So that's going to be our models for exponential decay and growth. So decay gets smaller, and growth gets bigger, and sometimes people call these graphs to be hockey sticks, where it depends on if you're left-handed or if you're right-handed. So here is again the model. Our goal today is to evaluate and graph exponential functions. So y equals AB to the power x is going to be our model, where A is the initial or starting value, B is the growth or decay factor, and x is the time period or the number of times you want to grow or decay. So here's a short example. Here is an exponential equation. Our initial value, A, is 10, and our growth factor is 2. Because this value is bigger than 1, this is growth. If it was a number less than 1, then it would be decay. So we're starting with 10, and our population is doubling every period. So let's try a couple of examples. In the exponential function y equals 1 times 2 to the power of x, what is the initial value? So again, we're working with y equals AB to the x, where A is our initial value and B is our growth or decay rate. So we want our initial value, so pick a letter. Our initial value is going to be A. Number 2, try this one on your own. We are looking for our growth rate. So we're looking at the 3. Our correct answer is B. Try number 3. Hopefully you remember what 2 cubed is. 8. So the correct answer is B, 16. So let's try a couple of word problems. Example 1, you deposit $450 in an account that pays 2.5% annual interest compounded yearly. What is the account balance after 10 years? So we are plugging in our y equals AB to the x formula, where A is our initial value, which is going to be the 450, and B is going to be our growth or decay rate. So we are earning money, so this is going to be growth. So if we plug in this as a decimal, 0.025, this number is less than 1. So we know we have to do something to this number because we want it to grow. We want the $450 to grow. So when we plug it in our formula, our initial value is the 450, and then we're going to do 1 plus that 0.025 to get our interest rate above 1. So when we're doing growth, you have to do 1 plus the rate, and if you were doing decay, it would be 1 minus that rate. So sometimes they tell you what that factor is, and then sometimes you actually have to figure out what that 1 minus r or the 1 plus r is. Let's try another one. A car is purchased for $20,000. The value of the car will be less each year because of depreciation. The car depreciates, which means to lose value, at the rate of 25% per year. Write an exponential decay model to represent the situation. So again, y equals AB to the x. So we're starting out with $20,000. But then we have to figure out what our depreciation rate is. So we lose 25%. But what percent of the value does the car keep? So if we lose 25%, it keeps 75%. And that's what's happening with this piece right here. We have to do 1 minus the R value. So that gives us our rate. So that's going to be the 0.75. So in this one, we just wanted a model. So that means it's going to have an X and a Y. Model kind of means equation. And then up on the top, we had to actually finish this calculation. So what I have right now is 450 times 1.025 to the power of 10. So if I put that on my calculator, I get $576.04. Just to double check, we started out with 450, and we need to make sure that our number increased because we were earning interest. Here's another real-world problem. You have 2 options for a savings plan. Which one is the better deal? Savings plan number 1, you start out with $20 and you save $5 every day. Plan number 2, you start out with $1 and you double your amount every day. So in both cases, X is going to stand for the number of days. We have to decide which of these is going to be an exponential model, and if it's not exponential, then what is it? So I see the word double. So that's going to tell me that I'm doing exponential growth. So y equals AB to the power of X. So I start out with $1, and I'm going to double every day. Whereas savings plan 2, I just earn $5 more every day. So that should tell us on day 0 we started with 20. On day 1 we get 25. On day 2 we get 30. So what happens here is we are growing linearly. So this is going to be a linear model where we're adding 5 every time. So our equation is going to be y equals, we start out with $20 and we add $5 every day. And if we write that in y equals mx plus b, we get 5x plus 20. So on the next slide, here's what I'm going to do. I'm going to use my graphing calculator and model these 2 equations. So the 5x plus 20, I'm going to my y equals button. And then 1 times 2 to the power of x. And you might want to have a time symbol in there. If not, it'll still do it. And then go ahead and hit graph. And you might need to hit zoom 6 or zoom 9 for the graph to find what you need. And if you don't have a graphing calculator, that's okay. But here's what your graph is going to actually look like. Where here's our exponential model, which is the red. So it's one of those hockey sticks. Sorry about that. And then the linear model is the straight line. And these graphs don't do straight lines very well. So we have to decide which one is the better deal. So let's investigate even a little bit further. So what I did was I went to my graphing calculator and I looked at my table. So if you look at the table, notice in y sub 1 we are adding 5 every time. So that tells us that this is the linear function, whereas over here our function is getting big fast. So what amount of days would be best to go with plan number 1? So to me it looks like in the green, that's where the purple column is going to be higher. The 35 beats 9, 40 beats 17, and so on. So what I'm going to write down is from days 0 to 5. In number 2, when does plan 2 catch up? Well, that would be on day 6, because all of a sudden it's at $65 versus the $50. What amount of days would be best to go with plan 2? So 6 days and up. So let's review our functions again. This is an exponential function where this is our growth rate. If it's bigger than 1, it's growth. If it's less than 1, it's decay. Determine whether each equation represents linear or exponential. So number 3, here's my A, here's my B, so this is exponential. Number 4, here's my A, here's my D, b, and this is exponential. So if we double check, is this one growth or decay? This would be growth. Number 4, growth or decay. This is less than 1, so this would be decay. Looking at number 5, well, this looks like y equals mx plus b, so this is going to be linear. And then number 16, oh, my x is an exponent, so here's my a, here's my b, there's my x. So this is going to be exponential because we're bigger than 1. This is, yep, you got it, growth.